Hello everyone. Today we're going to talk about field effect transistor amplifiers and switching circuits. Okay, they're very similar in construction to the BJT amplifiers and switching circuits that we looked at. The terminals are called different things. Are called, of course, gate, drain, and source instead of emitter, base, collector. But the concepts are very similar. As we talked last week about field effect transistors, or the last lecture, we know that the field effect transistor has a different transfer function than the BJT, right? The transfer function for a BJT is output current versus input current, basically collector current versus base current. With a field effect transistor, it's the drain source current versus gate source voltage. So it's a transconductance transfer function as opposed to a current, output current versus input current transfer function. We start with a common source amplifier, which is similar, excuse me, similar to the common emitter type amplifier. A common source has the source at near ground potential here. Notice the circuit looks very similar to a common emitter amplifier. Big difference is that the input impedance of this amplifier is much, much higher. It's in the nano ohms or micro ohms. It's very, very high. I'm sorry, mega ohms or even much higher than that as far as the input impedance goes. For BJT, it's going to be in the low mega ohms. This is in the high mega ohms for the common source FET amplifier. Okay, the output is taken from the drain here. Okay, the gain is not quite as high for this common source amplifier, but it's still certainly useful and practical. And here's the gain, the voltage gain down here is the transconductance times RD. Now this RD here is this RD. It's the drain resistor in combination with the load resistor. So we'll see a little later, a little equation for that. It's basically the parallel combination of the load resistor and the drain resistor. So if you notice, if you put in parallel these two resistors, this becomes a lower value, right? Because two resistors in parallel is a lower value of resistance than any single one of them. So as you load this circuit up with a heavier load, meaning a lower load resistor value, your gain goes down, and we'll see that in a minute. This slide talks about the admittance versus the impedance. Now, conductance is a reciprocal of resistance, and admittance is the reciprocal of impedance. You know, impedance is a complex resistance, if you will. It involves capacitance reactance, inductive reactance, and resistance. So data sheets for the field effect transistors normally specify the forward transfer admittance, which is little y f sub fs, rather than just transconductance. And here's a snippet out of a data sheet here, and it's in micromhos. So, and there's another expression for the gain here using admittance instead of the transconductance. Same thing, just substitute the admittance. Admittance is going to be conductance without, basically it's if at DC, admittance is the same as conductance. Okay. because the capacitive reactance and inductive reactance go away under DC conditions, right? So here's a transfer characteristic of our common source amplifier. This is the drain current versus the gate source voltage. And there's some pretty wide values for most JFETs. This is a 2N5458. And notice these numbers, the slide. These numbers vary widely, -1 to -7 volts here for VGS off. So it could be anywhere from over here, this slide here, or this curve here, to here. And this is the IDSS from 2 to 9. So it's pretty wide, right? So you got to be careful. Design your circuit to accommodate the worst case. We analyze a common source amplifier. We start with DC values. Here's a little example. The drain, what's the drain current here? Specification sheet, IDSS is 6 milliamps, VGS off is -4 volts. And you can plot this on this next slide. If you look at text example 9.2, this provides details on this. I'm not going to do that right now, but you can read the current and voltage at that Q point, 2.8 milliamps and -1.3 volts. If you have any questions on this example, please post it in the discussion board on our Canvas site. But it's pretty straightforward, and there is some homework on this too. So we have 2.8 milliamps and -1.3 volts for the Q point. That's the operating point. And if you capacitively couple the gate of this circuit, you'll ride up and down this curve here. And then you can, that's a graphical method, or you can use mathematical method to find it. The problem with that is, well, not only a problem, it's a little bit of a challenge, is it is a quadratic equation because ID is on both sides of the equation, you notice? It's kind of funny. But your calculator, if you want to look up how to do a quadratic equation in your calculator, which is, this is sort of a rudimentary example of how to do that. And you could, for whatever calculator you have, TI-54, whatever it is, you can look at YouTube videos to how to do a quadratic equation in your calculator. I encourage you to do that because it sure would come in handy for on an exam or something to be able to quickly do it. But here's what they end up with, 2.75 milliamps. And your VGS off, you have to enter a absolute value. It's not a minus, it's not a negative value. And so we go through it. So back here, end up with 2.75 million. So that was close. I think it was 2.8 on the graphical method. Okay. So we're looking at the gain here of this common source amplifier. So this is the transconductance, 3 millisiemens. And you get 2 millisiemens for the transconductance after you put in this part of the equation, which this is from chapter 8. And this is one of those equations, actually both of these should be on your equation sheet that you're using to do the homeworks. And this uses the RD sub D, which is 2.7K because there's no load. Okay, so it just uses the drain resistor here. Of course, the output is inverted. But yeah, put both of these equations on your equation sheet and use them to do the homeworks. So and for the exam too, the final exam. So if you're asked to find the voltage gain, this is the equation to use right here. And how do you find the transconductance? Well, this is how you find the transconductance, okay? And you'll be given all of these numbers, right? GM0, VGS, VGS off. So it really ends up being a plug and chug, okay? As long as you have access to the equations quickly. That's the important thing. And you've used them before. And as I said earlier, if you do put a load on here, okay, now you have to combine the drain resistor with the load resistor and your gain is going to go down. So how does that affect the gain? It goes down to 4.29, whereas before it was 5.45. So we went from 5.45 down to 4.29 just by adding that load resistor. If you add a heavier load, meaning a lower value of this 10K, maybe 5K, this will go down even more, of course. But notice how they've combined these two resistors. All right, it's the parallel combination of the two resistors. 2.7K and 10K, resulting in 2.13K. Okay, let's talk about the DMOSFET. These are used all over the place, and the reason is because they can operate in depletion and enhancement mode. It's great. You can AC couple the gate, right, and come up with a really nice little amplifier here. So the gate source voltage swings back and forth between positive voltage and negative voltage, and your drain current rides up and down the curve, the transfer curve. Very simple circuit, great amplifier. Okay, very high input impedance. All right, we're talking I keep saying it, mega ohms, many hundreds of mega ohms. Okay. The enhancement mode requires a bias. Okay, so you have to bias it in the positive, the VGS in the positive direction, high positive voltage. Which is okay, just adds another resistor here, and works the same way as the DMOSFET, except you have now biased gate, the positive voltage. Both are used. The DMOSFET's a little simpler. And here is a little multi-sim example showing the DMOSFET. Obviously, this is this probe here is at the front of this capacitor, because if it was over here, it would show that this curve would be offset by the bias, right, by this voltage divider. Shows a little gain here. Okay, common drain amplifier is similar to the common collector or emitter follower in our BJT. Okay, the common drain amplifier has the drain connected directly to VDD, and the output comes off here, the source. Okay. Now, remember the common collector amplifier, which was the emitter follower in BJT. What was special about that? It had a voltage gain of about 1. Remember, the output voltage was about equal to the input voltage. Only difference was this 0.7 volt drop across the base emitter. With the FET common drain amplifier, okay, it's a similar situation. Similar situation, except that the transfer function obviously is voltage out versus voltage in, but there's high current gain here, just like there is in the common emitter amplifier, but again, no voltage gain. So very similar circuits. And here's the voltage gain. And you could put on your equation sheet, common drain amplifier, voltage gain. There's the equation for it. So when you see this on the final exam, for example, if it's there, you'll get it right, because you have this equation right here. And voltage gain is always -1, but not much lower than -1. Okay, power gain is high. as we said. Okay, this cascode amplifier, it's a little unusual. I don't see these very often, but it combines a common source and common gate amplifiers with the gates at ground on this one. Don't worry too much about that one. They don't come along very often. There's a little multi-sim circuit for it. Pretty high voltage gain though, almost 100. Okay, Class D amplifiers are very important because they're everywhere. If you have any audio device at all nowadays, home stereo, your TV, your iPhones, any portable Bluetooth audio device, they all use Class D amplifiers. And the reason is because they're very efficient. They're switching amplifiers. They're the FET devices that drive the signal are either all the way on or all the way off. And those are the two most efficient places for any semiconductor device. When it's all the way on, it's saturation, for example, you've got no voltage drop across the device. So therefore the power dissipation is zero. The power is voltage times current. When it's all the way off, you have no current going through it. So once again, the current times voltage equation becomes zero. Of course, we don't completely get close all the way to those points, but they're close. So these circuits run very cool. So they do a little multi-sim example here, which we have a triangle wave generator here going into the inverting terminal of the 741 op amp. And then we have a sine wave going into the non-inverting terminal. And that results in this output here being a pulse width modulated signal. As the sine wave rides up and down the triangle wave, it will produce a varying output width on this output of the 741. And this is very common. I mean, you basically have a pulse width modulator is what this circuit is. And what you can do, this is the resultant output. So here's the triangle wave, and notice that here's the sine wave imposed on it. As the sine wave crosses each one of these thresholds, it produces a pulse width on the output of the 741. Now what you can do is filter this pulse width modulated output, and it will reconstruct the sine wave perfectly. Okay, notice that these pulses are wider, so if you put a capacitor that is charged on the output of the 741 op amp, it's going to be charged more often here, right? Because the pulses are wider, and therefore it lifts up the output, which produces this part of the sine wave, a higher voltage. Over here, the pulse widths are narrower, so therefore on the high side, so therefore the capacitor doesn't charge as much. So the sine wave, this part of the sine wave happens. So it's a lower voltage. And that's the low pass filter that does that. Very common circuit here, okay? These are Class B complementary MOSFETs. Class B, we learned that in the BJT amplifier section, right? We got a push-pull type arrangement here. And PWM is used not only in audio circuits, but as motor controls. All electric cars use PWM of some sort to control the speed of the motor. All right. The other good thing about controlling a motor with pulse width modulation is that the torque of the electric motor is preserved with speed, because the motor is basically being turned on all the way for a short period of time at lower speeds. as opposed to just being turned on a little bit with a lower voltage, and therefore you don't get the full torque. But you can by turning it on all the way, if you understand that. In MOSFETs, the other thing about MOSFETs used in these switching circuits is they got low on-state resistance, which adds to improves the efficiency. Okay, so they don't get hot. And finally, the analog switch. Now, this is something I've been working on at work, in my day job. This is really great because you can use these MOSFETs to turn on and off a signal path. So it's bidirectional. This could be in or out. That could be out or in. Okay. And the CD4066, which is some parts that I actually purchased the other day to do some experimenting at work for an audio circuit I'm working on. And I need to control and shut off the output during power down. Okay, because during power down, bad things happen and it results in a big pop going out into the speakers. So I'm going to try to put one of these circuits into my design and operate this control using a voltage supervisor chip to shut this off when power falls below a certain voltage. Okay, so nominally it's at 5 volts. As soon as it falls down below 4.7 volts, I'm going to open this circuit up, which is going to disconnect the output to my amplifier, which should, well, hopefully solve my power down pop problem, because it's really annoying. Very, very clever circuit, very common, and I'm excited. I'll let you know how it goes probably in a couple of weeks. Okay, that's it for this week. Again, if you have any questions, please post them in the discussion section. And if I don't talk to you, have a wonderful Thanksgiving, and we'll pick it up after that. One more lecture and then the final. Everybody stay safe and healthy.